Hello, everyone. My name is Filippo Pagani, and I am a postdoc at the University of Cambridge at the Biostatistics Unit. I'm going to talk to you today about a robust benchmark model with curved correlation structure for MCMC testing. Um, in general, assessing the quality of MCMC samples is very important and yet a very difficult task for both practitioners and MCMC developers. Problems that these people may face include, for example, questions like is the MCMC sample large enough, or did the chain mix well enough, or is the current algorithm the most appropriate one for the model I'm analyzing, and so on and so forth, right? This is all very general, and I'm going to talk today. I'm going to talk about these things slightly more in detail in the context of when the posteriors from the model have curved shapes. So why is that? Because curved shapes are actually more common than people think. This is an example from epidemiology. It's a posterior from a SAM model on Ebola data from a paper from a colleague of mine. And we were chatting about this, and we basically casually discovered that at least two of his posteriors have curved shapes, and the others don't look very nice either. So this is one example from epidemiology, and I have another example, actually two of them, one from astrophysics and the other one from cosmology. In these cases, it's probably even more important to know what you're doing, and because people in these fields use the uncertainty from the posterior to constrain the parameter space and rule out models of the physical world. So if you are getting the uncertainty in the tails wrong from your posterior, then you may rule out, good models, and the consequences of that may be quite important. Obviously, what benchmark models do we have to develop and tune the tools to make sure that the quality of our MCMC sample is good and the uncertainty of our posterior is correct? Recently, I've come across a few models, and I've sketched them down here, a few of them. So the first one is the two-dimensional Rosenbrock distribution that looks more or less like this. The middle one is a normal distribution and has been twisted according to a global metric that depends on sines and cosines, and this is the end result, basically. And the third one is an S-shaped distribution. These models are great, but they're not very flexible, I don't think, because what if I want to get an exponential-like shape? Or what if I want to get a posterior with a sinusoidal shape of some sort? It's not immediate to me how to extend these models to get these shapes and others that may be of practical interest to people. So, and even so, these are all 2D models, right? How do you extend these models to more than 2 dimensions? Let's focus, for example, on the 2D Rosenbrock here. It's a 2D banana, right? The most intuitive way to extend that to 3D is to actually think about a 3D banana. But if you think about it, if you look at an actual banana from below, the third dimension you just added is not curved. So how do you extend a 2-dimensional model to 3 or more dimensions, preserving the complexity you care about in the model and without breaking it? This is an important question to me. And to go on, let's focus a little bit on the 2D Rosenbrock distribution I was mentioning here. This is what it actually looks like in 2 dimensions, right? The mode is over here. And I cut the picture here 150 to make it look prettier, but in the end, this tail goes on to like 250 and probably more. Yeah, so this is the 2D Rosenbrock distribution. And then the problem is, how do we extend it to more than 2D, preserving the structure of the distribution? One simple way that comes to mind is we can take multiple copies of the same problem and then stack them together to build a higher dimensional posterior. And this is what the even Rosenbrock extension does substantially. And you can see here one copy of the original 2D problem here. This is the second copy of the original 2D problem. The problem is that these copies are independent from each other, and so their joint distribution will be round and not very interesting. And the higher you go in dimension, the more and more round distributions you will have. So this is not very desirable, and as well, I'd like to have some control over that. So we need to do something about it. One thing that people have done about it in the literature is extending the 2D Rosenbrock to more than 2D, following the full Rosenbrock extension, of which I'm not giving you the equation, but this is what it looks like. Okay, which has some desirable features, right? If you take these three pictures here and you put them together in your mind, you get a sketch that looks a bit like this. And this distribution, it is curved in every dimension that you can look at it from, which is what we wanted. The problem is that the model is misspecified. So as soon as you add a third dimension, the scale of the other two dimensions decreases way too much. And as I said before, it should go up to 250, and here it's 15. Okay. To give you a more precise idea, I have a plot here. So this is what the 2D Rosenbrock looks like, and this is what the first two dimensions on the 3D Rosenbrock extended to the full Rosenbrock look like. Okay, this is not okay. Our benchmark model should be more stable than that. Okay, we should have more control over it, and I feel like this can happen. This sort of thing happens generally with quite a few benchmark models. To summarize that, basically, many benchmark models can behave erratically when the dimension of the model grows beyond 2. The normalization constant is often unknown, and because of that, it's hard to draw a sample from the model. You can obviously use MCMC to draw a sample, but then if things change erratically, it's hard to tell if it's an MCMC problem or if it's a model problem. And even though the effective sample size, which is a common indicator to look at, it looks high, it may be that the MCMC is not actually leaving the mode of distribution. And you can obviously look at the tail ESS in this case, but then we're talking about a benchmark model, right? Things should be easier than that, at least in my opinion. And this is why I started working on the Hybrid Rosenbrock distribution. The Hybrid Rosenbrock distribution, its name comes from the fact that I've taken elements from both the even Rosenbrock and the full Rosenbrock distributions, and I put them together, and I've also managed to fix most of the flaws of those two models that each of them has individually. The Hybrid Rosenbrock distribution looks like this in 5 dimensions. As you can see, every 2D marginal is either a curved ridge or a straight ridge, and it's in general a very, very, very challenging distribution to explore. The other good thing, obviously, the details of that are described in this paper of mine that was recently published, and we managed to do that. We managed to not have round distributions here, unlike the even Rosenbrock case, because of the structure we gave to the distribution. It is as well, like the other one, divided in blocks, but each block of variables is not independent. They are all related with each other through the first variable. And we can add as many variables as we want in a block and as many blocks we want to the distribution. This is the equation of the Hybrid Rosenbrock. And because of the fact that it's written this way, it's also very easy to do the integral and to calculate the normalization constant. Because of that, we can draw an IID Monte Carlo sample very, very easily. And yeah, and like look at the shapes, calculate whatever quantity is not available in closed form, and that sort of thing. Yet another positive thing about this density is that I've taken as a template the classical 2D Rosenbrock here, but it doesn't have to be. We can just change this part of distribution here, this function, this link function here, to obtain very, very, very different shapes, whatever suits the needs of the practitioners or MCMC developers that are using this. For example, experimenting it a bit, I was able to obtain this kind of curved shape here with this kind of curvature. You can do even more complicated stuff using like sinusoidal waves, and this is a curve distribution with 2 modes, which is quite beautiful to me. So yeah, this is essentially the benchmark model, in my opinion, that people should be using more. The pros are it's very flexible. You can basically obtain any shape you want. Because of the way it's written, it's very, very easy to control everything about it, especially the difficulty that MCMC samplers can have sampling from it. And you can increase the dimension easily without breaking the model. And like I mentioned, it's very easy to draw IID and Monte Carlo samples, even like a huge number of one, and you can calculate any quantity that you need from them. And it also makes it very easy to visualize. Thinking about the cons, I can't quite come up with many, although it makes you think about what you're doing if you consider that as a cons. Once I sort of settled on the model with my co-authors, we set out to make some experiments, some comparisons of MCMC samplers. We compare the random walk metropolis, HMC, the nuts no U-turn sampler from STEN, and the simplified manifold Mala, which is a Mala algorithm that is defined on a manifold, and it's basically a very well-suited algorithm to sample from densities with curved correlation structure. We tuned the random walk metropolis optimally, as usual, with no variance covariance matrix, because there is no global conditioning that we can give to the algorithm that can represent all of the covariance structures of the target. And that's about the random walk metropolis. To differentiate HMC from nuts, we tuned HMC naively in the sense that we chose the parameters to maximize the ESS, the effective sample size per second, which sounds vaguely sensible, but only if the chain is mixing well on the target. If it's not mixing well, it's a terrible idea, and the results will show that. And on these four algorithms, we measured two things. The Kolmogorov-Smirnov distance on the cumulative distribution functions on each marginal, and then we took the highest, and also the Anderson-Darling distance on the CDFs of each marginal, and then we took the highest, the worst. We measured two different things because the KS distance, because of this soup here, it tends to pick up discrepancies closer to the mode of the distribution, while the Anderson-Darling distance tends to pick up, to be better at picking up the discrepancies in the tails of distribution. And every distance, as usual, has pros and cons, and that's why we chose to measure two of them to make sure we are not missing out on important details. Once we decide on what to measure, we run the experiments on a 5-dimensional hybrid Rosenbrock, on a sequence of 5D hybrid Rosenbrocks indexed by the parameter B. And roughly speaking, in this case, the higher the value of B becomes, the narrower the distribution becomes, and that makes it more difficult for MCMC samplers to sample from it. Let's look at the simplified manifold Mala first, which is the algorithm that is known to do well on these distributions, and so it's the one that we trust a little bit more. And looking at this progression here towards the distribution becoming harder and harder to sample from, the results are exactly as we expected. As the distribution becomes harder, the simplified manifold Mala has a little bit more troubles sampling from it, exploring it. Also mind that the distances on the y-axis are in log scale, so the differences between the algorithms are actually quite high. After the simplified manifold Mala, we can look at HMC and the random walk metropolis. Around HMC tuned naively and the random walk metropolis. Around the mode, surprisingly, they're both quite bad. And this is according to the Kolmogorov-Smirnov distance. While according to the Anderson-Darling distance, HMC explores the tails, naively tuned HMC explores the tails of the distribution slightly better than the random walk metropolis, but still not quite as good as it should. Once again, in this example, the simplified manifold Mala does exactly as expected here. One interesting point is that the nuts, the no U-turn sampler here, on both plots does actually basically equally as good or better than the simplified manifold Mala, despite having a conditioning matrix that is global and is fixed despite the correlation of the targets changing. That is because of the adaptive number of steps that the integrator takes when exploring the distribution. That feature helps a lot exploring this kind of density. And the results, you can see them in the plots. Around the mode, it basically does as well as simplified manifold Mala, and in the tails, it does even better than that, which is a very interesting result, at least for me. As summarizing what we're talking about so far, measuring the quality of MCMC output is a very, very important thing. And I feel good benchmark models that help developing effective tools are very, very important as well. The Hybrid Rosenbrock is now a quite robust benchmark model that can help people developing good tools and testing them and finding the breaking point of those tools, because that's an interesting thing to know as well. And if you're interested in this sort of thing, on my GitHub, I have a Jupyter notebook with our code in it that you can use to play around to see what can go wrong running that sort of algorithm, this sort of algorithms on a target like the Hybrid Rosenbrock, and you can at least look at the same situation from different perspectives. Also, in the Jupyter notebook, you can find my plotting code, which is quite useful in my opinion, and feel free to use it for your own research. Thank you very much for listening. Bye.